Okay, so we're going to go back to the do now question here, the contest question problem 3, and hopefully you follow the instructions very carefully. You're drawing any electric and or magnetic fields produced by any of these objects. Let's start with electric fields first. So what object here would create an electric field? So hopefully you picked like letter F. What is letter F? It's a positive point charge. Is it a proton? I don't know, it doesn't really matter, but it's something that has a positive charge, and so of course we know we would test for its electric field with a positive test charge. We would repel that, and so we'll draw some electric field lines. It's always arbitrary how many you draw. I just chose to do 4, like this, in this nice pretty pattern. Now on my screen, I'm color coordinating everything. Hopefully you've been noticing that. I'm always using red for electric field lines and blue for magnetic field lines. If you don't have colored pencils or ink or something like that, just make sure you absolutely show that this is an electric field by putting capital E next to it. And of course letter G is another positive point charge, so it's going to create an electric field. It looks exactly the same. The only difference here is that the charge is in motion, but that certainly did not affect its electric field. The only thing is that this electric field is sort of localized around the charge, and so if the charge is in motion, maybe you'd feel a change in the electric field depending if it's moving towards you or away from you. But the picture is exactly the same, and again, make sure we're labeling it with a capital E. Of course, letter B is another point charge. Is an electron? I don't know, but certainly would attract a positive test charge, and so all electric field lines point radially inwards, where again it's arbitrary how many field lines you draw. Just make sure you are labeling it with capital E so we know it's an electric field. Is there anything else that creates an electric field? Hopefully you said no. There's absolutely nothing else here creating an electric field. Just because there's a wire with current doesn't mean that there's an excess charge, right? For every proton that enters over here, there's a proton exiting over there. It doesn't accumulate some sort of excess charge. So how do we know if anything is going to create an electric field? It has to show that it has an excess charge by putting a positive or negative sign on it. That's how we know it creates an electric field. Okay, so what creates a magnetic field? Well, definitely letter A, there's a wire with current, and so to draw its magnetic field, we're doing a right-hand rule, right? And so is this the pointing or the grabbing one? I hope at this point you recognize it's the grabbing one, so you know my advice, lay your imaginary wire, your pen or pencil up against your paper, put your right hand with your thumb pointing to the right, you're going to try to grab that wire. You should definitely feel your fingers hitting the page below the wire. That's where the X's are. You pull your imaginary wire up off the page, wrap your fingers around underneath. You see your fingers poking up out of the page. That's the dots. And so here's the magnetic field, where again I'm color coordinating as blue, but if you don't have that, absolutely make sure you have the capital B there so you know the difference when you're looking at the page, we're looking at electric fields or magnetic fields. What else? Well, letter D, there's another wire with current, right? This time we're grabbing it so our thumb is pointing to the bottom left of the page, as we have X's on the top left and the dots on the bottom right, where you feel your fingers hitting, right, like that. I always find it's kind of interesting if you are in college and you're taking an electricity and magnetism course. When you're in the introductory courses, hundreds of students usually take it at the same time, and to house you for these large exams, they usually put you in like a gymnasium or a large auditorium or something like that. And so if you just sort of sneak a peek out of the corner of your eye, you'll know when everyone gets to the magnetism part, because you'll see everyone doing weird twisty things with their hands, contorting them in weird ways, and getting cramps in their hands and like that. And then off in the distance you'll see one poor student using their left hand to do the right hand rule, and your heart just goes out to them. So just make sure you're always using the right hand when you do these right hand rules. Alright, so what else is creating a magnetic field? Well, we got letter E, right? Here's a wire with a current, and the current's pointing out of the page. So you try to grab that wire, your thumb's pointing out of the page, you wrap your fingers around, so it's going to be circles, and they're pointing in a relatively counterclockwise direction. Now, notice I haven't been using the loops around the wire here, but certainly that's equivalent. If you'd drawn the loop here going around like that, or this loop here going around like that, that's fine as well. But we like the dots and X's. What about dots and X's here for letter E? Where would the dots go? Where would the X's go? Why don't you pause the video and give that a minute to think about. So hopefully you recognize you can't do this with dots and X's, right? This wire is sort of poking up through the plane of the paper. Your hand, as you grab that wire, is in the plane of the paper. At no point do your fingers hit the paper, which is why I always want you to do this with your paper and have that very tactile sensation of your fingers hitting the page. That's where you know the X's are going to be on which side of the wire. But you can't do that with this one. Okay, what about letter C? What is this object? Right, it's a solenoid or electromagnet. We know our first step in doing this is tracing the current. So we know here's our positive terminal, charges come out of here, and so anywhere in these nearer parts of the wire, the charge is moving to the top of the page. That's an essential step in doing any electromagnet or solenoid problem. At this point, you can do your right hand rule shortcut if you like, or you can do your grabbing of the wire. My suggestion, grab the part of the wire that's close to you where you can see the charges moving. Just remember, all we really care about is the magnetic field in the interior of the solenoid, bounded by the loop. That's where all the field lines are clustered together, and the field line is pretty much uniform and nice and strong in there. And so really that's the part we are considering when we stop our fingers inside, or with the right hand rule shortcut, your thumb should be pointing to the left as the magnetic field points out of this end into this end. If you want to complete the picture of it looking like an electromagnet, you might want to draw some magnetic field lines on the outside, make it look like a bar magnet, in which case this is clearly the north pole, this is the south pole of our electromagnet. Does anything else create a magnetic field? Well, hopefully you recognize that letter G is creating a magnetic field, because here we have a charge in motion, right? If that's bothering you, imagine it's a whole bunch of charges all moving to the right, positive charge moving to the right, and encase them in a wire. And now, if you were to grab that wire with your thumb pointing to the right, well, that would be exactly the same picture as letter A, wouldn't it, right? And so let's put a dot above and an X below. And here you see why it's so essential that you're labeling which field is which. So you look at this picture, you can tell there's an electric field and a magnetic field. I'm only putting one dot and one X because it's rather localized around this charge. As the charge moves, it sort of takes its magnetic field with it. Does anything else create a magnetic field? Hopefully you recognize letter B does. Here again is a moving charge, but this is a negative charge, right? We can't do our right hand rule for that one, but we can say negative charge moving to the left. That's like a positive charge moving to the right, which means it's exactly the same picture as letter G or letter A, where I draw one dot and one X because it's rather localized around this charge. As it moves, it sort of takes its field with it. So what about letter F? Does it create a magnetic field? Well, of course it doesn't, right? Because the velocity is 0. And so we could see that charges, objects that have a net charge, create an electric field. If they're moving, they also create a magnetic field. Okay. So we see there's sort of a progression here. Here's a point charge that's not moving with just an electric field. Here it has an electric field, but since it's in motion at a constant velocity, it creates a magnetic field. What if instead of having constant velocity, it had a changing velocity? So we've got one more space here, although we're going to draw a rather large picture. So you may want to change over to your handwritten notes to draw what happens next. I'll be using all this space to draw this. Alright, so let's say we have an oscillating or vibrating point charge. So here's our positive charge. Let's say it's shaking back and forth, oscillating back and forth, back and forth, back and forth, back and forth. And we're going to set up an observer over here to watch this as it moves and what sort of happens to its fields as it goes. So let's say we're drawing a person's head and we're watching them from a top-down view, and you're saying to yourself, he's not going to draw this on the PowerPoint. Yes, I am. So here's the person's head, and there's their shoulders, and their arms, and their torso, and their hands coming out of their sleeves, and there's their legs, and their feet, right? So there's their head, shoulders, knees, and toes, right? So you can just draw a smiley face for all I care, but there's our observer. Now, obviously, this is not to scale, otherwise this is the tiniest little observer you saw, or this is the largest point charge you ever saw, but regardless, this person is recording what is happening to this charge's fields as it moves back and forth for these large oscillations. Let's think about an electric field first. Right? And so here's the charge moving farther and farther away from the person, and we know since it's a point charge, E equals kq over r squared, so as r increases, the field gets weaker, right? And it stops and turns around, and it gets closer and closer, so now r is the distance of closest approach, and so as r gets smaller, the field that this person would register is getting stronger, and then it goes all the way over here, so it's weaker, and stronger, and weaker, stronger, weaker, stronger. It's going to go back and forth, back and forth. Let's see what this would look like on a graph. So here's going to be the axis of the graph, which is tilted a little bit, and you'll see why that isn't just a little bit. And so the field gets stronger and weaker and stronger and weaker and stronger and weaker and stronger and weaker. And so the field, electric field, is going to oscillate in sort of this sinusoidally varying pattern. Back and forth, back and forth. Okay, let's talk about magnetic fields. We know it's going to have a magnetic field when it's in motion. So we know if it's going back and forth, it's like simple harmonic motion, so it's going very fast here, and then it slows down, and it comes to rest, which means the magnetic field is getting weaker and weaker, and then turns around and speeds up, and here it's going the fastest, so its magnetic field is the strongest, but it's got to slow down over here, so it's weaker, stronger, weaker, stronger, weaker, stronger, weaker, stronger, and so the magnetic field is going to change in a very similar pattern, getting stronger and weaker in the same locations where the electric field got stronger or weaker. So we're going to draw that on the axis as well, but it gets a little more interesting. So let's go back to this picture with problem 3 here. Let's take a look at this picture, right? The electric field is in the plane of the paper. The magnetic field is pointing into or out of the paper. And so the electric field here is pointing straight up, and the magnetic field is pointing towards you. Over here, the electric field is pointing down, and the magnetic field is pointing away from you, right? So what orientation is there between magnetic field and electric field? Well, they're at right angles to each other, aren't they? They're perpendicular. And so in this picture, the electric field is going to oscillate in sort of a vertical orientation. The magnetic field is going to oscillate in a horizontal orientation, like this. Back and forth and back and forth. And there's the magnetic field as opposed to the electric field. And if you're having trouble visualizing this, we can put some arrows on this. Here are some arrows pointing up and down to show the magnitude of the electric field. Here's some arrows pointing left and right to show the magnetic field. Okay. Now, it turns out that this effect, this changing electromagnetic field, doesn't just stay here. It actually transmits and travels through space. So the axis could actually be a vector here. I'm going to put a vector arrow there showing that this effect, this changing electromagnetic field, actually propagates through space. this vibrating electric charge will actually radiate this changing electromagnetic field. So I'm dropping a lot of clues here because it turns out we've seen this effect before. This oscillating, this changing electric and magnetic field, which is oscillating back and forth in a picture that looks sort of an awful lot like a wave, doesn't it? Right? Doesn't it remind you of a wave? Right? So we have a wave created by an oscillating electromagnetic field produced by a vibrating, accelerating electric charge. We've seen this before. What is this? Well, hopefully you recognize this is light. Yeah, right? Light, an electromagnetic wave that travels through space, produced by accelerating electric charges. And so you see, it all comes together. Everything comes full circle. This discovery that vibrating or oscillating electric charges create electromagnetic waves, which are the same thing as light if they're in the visible spectrum, this was first discovered in the mid to late 1800s. And this was a time when physicists around the world realized all these connections among things in physics. And they figured that with Newton's laws and conservation of energy, conservation of momentum, they could actually do pretty much any mechanics problem they could think of. And with the equations of electricity and magnetism, which were put together by James Clerk Maxwell under just 4 equations that describe pretty much everything in electricity and magnetism, they could do any problem in electricity and magnetism. And with this connection between electricity and magnetism and then connecting it to light, everything seemed connected. So at the end of the 1800s, physicists around the world thought they were done, that physics was done. They closed the book on everything and they said, oh, let's just solve some problems here. It turns out they were wrong. This is the end of what we call classical physics, and the beginning of then modern physics. And that's a story for another day, but it turns out that what they thought was the end of physics was really just the beginning.